By 1957, it became clear that the night sky, far from being a mere visual wonder, is a reflection of the staggering forces that govern the cosmos. Each star, nebula, and galaxy is a participant in a grand cosmic dance dictated by the laws of physics, motion, and energy. The universe is constantly in motion, teeming with activity and mystery, much of which remains beyond our comprehension. Despite centuries of exploration and scientific advancement, countless questions remain unanswered. We are left to wonder about our place in this immense system. Why do we exist? How did planets and stars come to be? What other possible outcomes might the cosmos have entertained in its vast timeline? Human nature often leads us to overlook cosmic phenomena until they become pressing or potentially dangerous. Our gaze tends to shift only when events in the heavens start to have real or imagined consequences here on Earth. One such example is Betelgeuse, a massive star in the constellation Orion that has recently begun to show signs of instability. This celestial giant has been trembling in a way that suggests something significant and potentially ominous may be unfolding. Betelgeuse is not just another star in the sky. It is a red supergiant, a colossal celestial body whose sheer size dwarfs that of our Sun, making our own star appear minuscule by comparison. Located over 640 light-years from Earth, Betelgeuse's apparent brightness in our night sky belies its true distance. In cosmic terms, 640 light-years is a vast expanse. Traveling at the speed of light, it would take more than 6 centuries to reach it. With today's technology, realistically, it would take over 12 million years to cover that distance using conventional spacecraft, a span of time far exceeding the entirety of human history. This puts into perspective the extraordinary magnitude and power of this distant star, which has been exhibiting intense trembling and instability for some time. Although stars appear serene from Earth, they are anything but calm. Regardless of their size, stars are dynamic systems governed by complex physical processes. Scientists have long studied Betelgeuse due to its pulsating nature. It is classified as a variable red supergiant, meaning its brightness fluctuates over time. These pulsations are driven by internal mechanisms that cause the star's luminosity to vary in cycles ranging from tens to thousands of days, depending on whether it is expanding or contracting. These variations make Betelgeuse an object of intense interest, particularly since its changes in brightness are unusually pronounced. Its magnitude has been observed to fluctuate between 0 and 5, a remarkable range that reflects the star's volatile nature. Betelgeuse's brightness variations follow specific cycles. The shorter cycle lasts approximately 185 days, while the longest spans over 2,300 days. These cycles can be measured with great precision and have offered astronomers critical insights into the inner workings of the star. In February 2021, the star's V-band brightness dropped to 1.1614, one of the lowest levels recorded in years. This anomaly deviated sharply from its historical pattern and triggered concern and further observation, as it hinted at deeper changes occurring within the star. Betelgeuse's striking red hue adds to its intrigue. This color results from a relatively low surface temperature of around 3,500 Kelvin, significantly cooler than the Sun's surface temperature of approximately 5,500 Kelvin. Despite its massive size, this lower temperature means Betelgeuse emits less energy per unit area than our Sun, which paradoxically makes it appear less luminous in certain contexts. What makes the current situation more alarming is that Betelgeuse, while typically stable for a red supergiant, has recently transitioned into a more volatile phase. This shift is believed to be tied to changes in its core. As with all stars, the fusion of hydrogen into helium fuels Betelgeuse's energy output. However, in red supergiants nearing the end of their lives, the hydrogen in the core becomes depleted. This depletion causes the star's outer layers to expand as the core contracts, leading to increased instability. During this stage, helium begins to accumulate around the core, initiating a new fusion process known as helium shell burning. In this phase, helium atoms fuse to form heavier elements such as carbon and oxygen, releasing bursts of energy that counteract gravitational collapse. Unlike hydrogen fusion, which occurs more steadily, helium fusion is erratic. This irregularity causes bursts of energy to build up and release impulses, disrupting the star's structure and creating powerful stellar winds. These winds expel vast amounts of material from the star's outer layers, a process that further alters the star's internal balance. As a result, Betelgeuse's outer shell undergoes continuous expansion and contraction, a rhythmic phenomenon we observe from Earth as changes in brightness. This pulsating behavior is akin to a cosmic heartbeat, revealing the turbulent life hidden beneath the star's surface. To understand these phenomena more deeply, astronomers rely on two key observational techniques: photometry and spectroscopy. Photometry involves measuring the star's light output over time, revealing patterns in its brightness and helping track the pulsations of stars like Betelgeuse. These light curves provide a direct window into the star's behavior, making it possible to detect changes that may not be immediately visible to the naked eye. Spectroscopy, on the other hand, analyzes the light emitted by the star across different wavelengths. This method uncovers details about the star's temperature, composition, and motion. When Betelgeuse pulsates, its spectral lines shift, revealing crucial information about the internal processes driving those pulsations. By combining data from photometry and spectroscopy, scientists can construct detailed models of stellar behavior. These models use the laws of physics, including equations governing fluid dynamics, thermodynamics, and nuclear fusion, to simulate the inner workings of stars. Using powerful computers, astrophysicists can test how various internal conditions affect a star's pulsations and predict future changes in its structure and luminosity. These simulations bridge the gap between theory and observation, allowing researchers to test hypotheses against real data gathered from telescopes. One especially fascinating process within Betelgeuse is stellar convection. As energy is produced in the core through fusion, it moves outward toward the star's surface. In red supergiants, this energy transport occurs through convective currents. Hot plasma rises from the interior toward the surface, while cooler material sinks back down, forming a churning, dynamic system that transfers energy through motion. These convection currents cause fluctuations in the energy reaching the star's outer layers, affecting its brightness. When more energy reaches the surface, the star appears brighter. When less energy arrives, it dims. This dynamic transport of energy contributes significantly to the pulsating nature of Betelgeuse. These pulsations are not mere random fluctuations but often follow discernible patterns, especially in variable stars like Betelgeuse. The cycles of brightness are intricately linked to the expansion and contraction of the star's outer envelope. As the star expands, its surface area increases, causing the outer layers to cool and darken. As Betelgeuse approaches the final stages of its stellar life, these pulsations and convective processes become more pronounced. The interplay of fusion, convection, and radiation inside the star leads to a delicate balance of forces, a balance that, once tipped, could culminate in a dramatic conclusion, a supernova. The scientific community continues to monitor Betelgeuse with keen interest, knowing that we might be witnessing the slow, spectacular death throes of a star. As Betelgeuse edges further into this volatile phase of its existence, astronomers worldwide are constantly captivated by its subtle but unmistakable transformations. Each dimming event, each slight shift in spectral lines, offers clues to the deep interior processes at work within this cosmic colossus. The star's behavior continues to challenge our models, urging refinement and deeper exploration of stellar physics. In this stage of its life, Betelgeuse is effectively unveiling the final act of a great star. Its shells are hydrogen and helium burning in episodic surges, its convective currents reaching deeper and more violently into its interior, and its outer layers puffing outward and collapsing inward in a rhythmic drama unfathomably vast. This drama is not happening in isolation. Betelgeuse exists within the Orion constellation, amid a tapestry of stellar nurseries, nebulae, and other vibrant celestial phenomena. The famous Orion Nebula, an immense cloud of gas and dust where new stars are being born, lies close by in the sky, reminding us that death and rebirth are inextricably linked in the cosmos. Betelgeuse's deep red glow stands in contrast to the brilliant blue-white stars Rigel and Bellatrix nearby. These stars, younger and less massive, represent different stellar life cycles. Rigel, a blue supergiant, may explode sooner than Betelgeuse, showing us how mass and age dictate destiny in stellar evolution. Our familiarity with Betelgeuse is also colored by human history. Ancient astronomers from cultures across the globe noted this bright red star long before telescopes. The Greeks associated Orion with a mighty hunter. Native American tribes wove stories of creation and cosmic balance around it. Arab and Persian skywatchers tied it to seasons and agriculture. In each culture, Betelgeuse took on symbolic meanings tied to power, fate, or change. Today, we connect with the star on scientific and emotional levels alike, marveling at its physical processes but also recognizing in its cyclical rise and fall metaphors of mortality and transformation. In modern times, Betelgeuse gained global attention in late 2019 when it underwent an unprecedented dimming event. Televisions and social media lit up with speculation. Was Betelgeuse preparing to explode? Numerous amateur astronomers recorded the dip, while professional observatories rallied to gather data. Multi-wavelength observations, from optical and infrared